Okay, let's go ahead and start section 2.6, rational functions and asymptotes. I am going to split this up into several videos just so I don't have one incredibly long video. So let's start with the definition first. A rational function is a function of the form where f of x equals, and then you have just a ratio of two functions, a numerator function, if you will, and a denominator function, where both of these are just polynomials. So again, it's just a ratio of polynomials. That's all a rational function is. So where n and d are polynomials, and d of x is not the zero polynomial, which means d of x cannot be zero. Again, can't divide by zero. All right. So the domain of a rational function consists of all real numbers. Because again, polynomials, we can put any number in, except those x values for which d of x is zero. So in other words, I can't plug any number into the denominator that would make that denominator come out to zero. Example one, find the domain of f of x equals 1 over x and discuss the behavior of f near any excluded x values. So this is kind of an important problem, and it comes up quite a few different places. The idea that whatever numbers we throw out of the domain become what we call excluded values. And what happens near those excluded values is extremely important. So the domain of this function, it's going to be all real numbers, except x equals, well, this is a pretty basic one. It's just that the denominator is x only. So the denominator would be 0 if x was 0. So the domain is any real number except for x equals 0. So what I want to do is I want to take x values near 0, okay, but not 0. So we're going to start with something like, we can go 1, and then maybe 0.1, and then 0.01, and then 0.001. Okay? And let's take a look at what f of x is if I do that. So put 1 over 1, I get 1. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000. And so what we'll see is this, that as x approaches 0, now there's a little thing that we're going to do here that we'll do, you're going to see a lot more of it next year in calculus. And that's this, that there are two directions from which we can approach 0. Okay, if you imagine a number line, 0 on the number line, there's a left and there's a right of 0. So we can approach 0 from the right, which is what we did here. Okay, 1 would be out to the right of 0. 0.1's a little closer, but still to the right. 0.01 is even closer, still to the right. So as x approaches 0 from the right, the function, it gets larger and larger and larger. I mean, if we had more values here, where I had 3 zeros and then a 1, the answer would be 10,000. So the function goes to infinity. Let's also do the same and approach x from the left. That is, I'm going to start at -1, and then -0.1, and then -0.01, -0.001. And so let's look at what happens as x approaches 0 from the left. And again, 1 divided by -1 is -1. 1 divided by -0.1 is -10, -100, -1,000. And so we can see here that f of x is approaching minus infinity. Okay. So what we could say is this, that as x approaches 0 from the right, f of x approaches positive infinity. And the phrasing that we use quite often is this, that it increases, because it's going up, and it never ends. And the phrase is without bound. And the idea, if you think of like a boundary, would be something that you can't go past. Well, this is a case where there is no boundary. It's just going to go up forever. And so we would say in this here, as x approaches 0 from the left, that f of x approaches negative infinity, that is to say, it decreases without bound. Let's take a look at example 2. For which values of x is this function undefined? Well, again, when is a rational function undefined? It's undefined when the denominator is 0. So all I care about in this case is when will x squared minus 16 equal 0? Now, there's a couple different ways of solving this. What I want to do is I want to push you guys in the direction of solving it by using what we call here a difference of two squares to factor this. So this would factor, well, we have an x and an x to give us the x squared. And I would need a 4 and a negative 4 to multiply to give me the negative 16, and then to cancel out the outers and inners. Next, we have a product equal to 0. That only happens when one of the factors is 0. And so x equals negative 4, and x equals 4. So to answer the question, for which values is the function undefined? So f of x is undefined at x equals positive or negative 4. Just a real quick aside, the other option is to set x squared minus 16 equal to 0, add 16 to both sides. And then when you do the square root, just remember to do both the positive and negative square root of 16. I know it looks a lot easier, it's very attractive, and I will never tell you not to do it this way, but there's so many times where we're going to need to be able to factor a difference of two squares that it's worth just getting that practice in. All right, x and y intercepts, we've worked with these for years. But think about a fraction for just a second. If I have a over b and I say, when is this fraction equal to 0? The fraction is 0 when a is 0 and b is not 0. Because again, b can't be 0, period. But there are times we're going to see when it would be, and we have to work with that and everything. But in this case here, we're focusing just on when a is going to be 0. So the function has an x-intercept whenever the numerator is 0, but the denominator is not 0. A rational function can have any number of x-intercepts, and by any number, we mean that there could be 0, 1, 2, 3, 4, as many as you want. The function f has a y-intercept at f of 0. So again, we want the x to be 0. A rational function can have 0 or 1 y-intercept only. It can never have more than one, otherwise it fails a vertical line test. If the numerator and denominator are expanded out, then the y-intercept occurs at the point 0, comma. Now, this a0 over b0 is just the constant terms of both the numerator and denominator. And we'll see that in the next one. All right, so let's find some x-intercepts first, and then we'll find some y-intercepts, and that'll end this first video. So find all x-intercepts of this function. So the first thing we're going to do, and you're going to see this in every single one of them, our first job is to factor. So x squared minus 2x minus 1 factors to x minus 1 and x minus 1. And the denominator is x minus 8 and x minus 1. I'm going to go ahead and write that numerator is x minus 1 squared, x minus 8, and x minus 1. Now, the numerator, x minus 1 squared, equals 0 when x is 1. That's the only time the numerator is 0. But 1 also makes the denominator 0. So we can't have that. All right. So in this case, because there's no value that makes the numerator 0 but doesn't make the denominator 0, then we would say there's no x-intercepts. Now, you've got to be extremely careful here. What I'm going to do is I'm going to switch over to Desmos. And what you're going to see is you're going to see the graph of the function. And hopefully the first thing that you see is that it certainly looks like there's an x-intercept. So here we see the function, and as it comes down, it certainly looks like there's an x-intercept. I mean, when we click off it, you come right over, and it looks like there's a point there. And if I click on it, it says 1, 0. Okay, but this is where it shows you the deficiencies of these graphing utilities. If I click out here and I come up and I move this point over that, watch what happens to that point as it hits 1, 0. And watch it not do it now. Let me click off and do this here. Okay. Of course, it's not doing it. Okay. So what it normally shows, it should show a hole in the graph of this function at 1, 0, and say that it's in the coordinates would be 1, comma undefined. But the issue is that it's hitting the x-axis here, and I don't know why this graph does it. But again, if I put 1 into this function, I get 0 on the top, I get 0 on the bottom. This is undefined. So there is no x-intercept. It doesn't matter what Desmos is showing us here. Okay. Last, let's show the y-intercept. So again, to get the y-intercept, all we do is we do f of 0. Now again, I'm going to show you the steps. I plug 0 in. But I hope you can see that all three of these terms here, 1, 2, 3, end up becoming 0. So we get just the negative 64 over the negative 32, which is 2. So my y-intercept is at the point 0, 2. All right, I'll continue in just a second on the next video.